Okay, so let's continue. The next speaker is Jonas Schober, a Levinson type theorem for scattering matrices with varying dimension for Schrödinger operators on the discrete lattice. Please, Jonas.
Thank you, and special thanks for Miguel and his team for organizing this very nice conference. Um, Also, probably of all the persons Miguel talks about, there is none he talks that good about as Volker. And when I finally met him a few months ago, I could confirm everything that Miguel told me about him, and I came to like him a lot. So I'm grateful I can be here for celebrating his birthday, and congratulations also from my part. Um, Today I will talk about a model I was studying with Miguel the last 2 years, and we're talking about a scattering theory on a one-dimensional lattice and discrete line. So the outline of the talk is roughly following. In the beginning, I will give you like a program I want to do for scattering theory, and then I explain you my model and how things are concretely done in this concrete model. So, okay. So what is scattering theory? Well, as we have seen in many talks, if we want to do quantum physics and we have a dynamics, then we consider a complex Hilbert state, a vector in this Hilbert space we call state, and then the dynamics is modeled by e to the minus ith for some Hamiltonian, which is a self-adjoint operator on that Hilbert space. And what is scattering theory? Well, we take the real Hamiltonian or interacting Hamiltonian and compare it to an ECR dynamics given by H0, which is free Hamiltonian. And concretely, we are interested in if the following operators exist, which is basically you play the two dynamics one against each other, take the limit, and on the end, you project to the absolute continuous spectrum. Why do you do that? Well, if you have an eigenvector, then the limit can just exist if it's a simultaneous eigenvector for the two, and then it's basically decomposes in a trivial part. And so we are interested in if these operators exist and calculate them if so. When do they exist? Well, there are many results about that, but the specific one we will use is the Kato-Rosenblum theorem, which basically says that if the difference of these two is small, in which sense? Well, that the difference is trace class, then the wave operators exist and are in fact partial isometries from the absolute continuous spectrum of H0 to the absolute continuous spectrum of H. Okay, oh, sorry. Well, and if both of these operators exist, then we are interested in combining them. So we define S to be omega minus star omega plus, which kind of relates the data at minus infinity, the data at plus infinity. Okay. Well, and especially if H0 has a purely absolute continuous spectrum, then the Kato-Rosenblum theorem guarantees that it's a partial isometry from the absolute continuous spectrum, which is the whole Hilbert space to itself. So it's a unitary operator. And this will be the case in the model we will look at. Okay. Now, what else? Well, if this operator exists, then one can easily show that it commutes with the operator H0, which means that you can simultaneously diagonalize them. So if you decompose the Hilbert space as a direct integral, such that the operator H0 is then of the form of multiplying in the energy E in the Hilbert space HE, then the operator S also decomposes with respect to that integral. So it's of the form of integrating over the absolute continuous spectrum over some operators. And since S is unitary, all these operators SE over which you integrate will also be unitary. And then given this, the operator SE is called the scattering matrix of the energy E. And our goal is to, in our model, we will try to calculate this explicitly. Another thing we want to do, which appeared in the title, is the Levinson type theorem. So what is that? Well, the first thing is you consider this function E maps to SE, and the first thing that considers a Levinson type theorem is the proof that this is in some sense almost everywhere differentiable. And then once you have that, it's calculating this integral over the logarithmic derivative of the determinant of this matrix SE, and somehow make sense of this integral if it doesn't exist in a traditional way, and then calculate its value and see if you can recover some data from that integral. So that's the problem. That's the program what we want to do. And now I introduce our concrete model, and well, we'll try to do all of these things. So what is our model? We consider some natural number, some integer L, and the other input is invertible normal matrix A, L times L matrix. And then our Hamiltonian H0 is on the L2 space on Z with values in C to the L, and is given by the value in some point n is you take A star from the point n plus 1 and A times the value in n minus 1. Our motivation for this model is purely from mathematical reasons, because as you see later, there's some interesting properties. But if you want to think physically about this model, you can imagine something like having a one-dimensional crystal where in each point you have in each integer you have an atom, and every atom is interacting with the two atoms on each side. And then L would be something like the internal degrees of freedom of an atom you spin or something, whatever you prefer. Okay. Well, this is H0, so I have to explain what's the interacting Hamiltonian. So we take a potential. In each integer, you have self-adjoint matrix. And we require this potential to satisfy the following growth conditions. So it's essentially that the first momentum of the potential has exponential decay, where the basis of that exponent is defined by the matrix A. So you take A times the norm of the inverse of A. Remember that A was an invertible matrix, and then you take this function here. I will later comment why we choose this this growth condition. Okay. Okay, and then we define H to be H0 plus this potential V. Well, and we want to do scattering theory, and one can easily see that this growth condition implies that also the sum of all the potentials is finite, and that means that this V is in fact a trace class operator, and therefore by the Kato-Rosenblum theorem, wave and scattering operators exist and satisfy all the properties that we discussed before. Okay. What we will now do is we simplify the model. So we showed it by some suitable unitary transformation. We can make a bit simpler model out of that, which will make very many calculations we do later much easier, but we don't lose any information by that. So what we do is we do the polar decomposition of our matrix A, and since A is normal, we can use the same unitary on both sides. We do the left or right polar decomposition. Okay, and then the unitary operator on the whole Hilbert space that we will consider is in position n, we multiply from the left by u to the n. And if you do that, you can calculate what happens if you conjugate a H0 with that operator, and it turns out it gives you basically the same Hamiltonian, but you just get the absolute value of A, which you transform out the phase. And then you do the same with the potential, and it turns out, well, there you just conjugate the potential of some unitary. So this shows that if you replace A by the absolute value of A and the potential by this conjugated potential, then without loss of generality, we can assume that A is anyway a positive matrix, because by unitary transformation, we can transform one to the other. Okay. And notice that this quantity, the base of this growth condition as we had is invariant under this transformation. It does not change because anyway it just involves the norm of A and the norm of A inverse, which don't change if you take out the phase. And also the norm of this new potential is just the same as the old one, so growth conditions are not affected, which means that this condition is unchanged. So also this where we can just do the transformation without changing anything about the model. Okay, we will do one more simplification. Since it's a positive finite dimensional matrix, we can diagonalize it, so we can, without loss of generality, after doing some base transformation, assume that it's already in diagonal form. And well, after another change of basis, we can assume that the eigenvalues are ordered by size, where A1 is the biggest and AL is the smallest eigenvalue, but bigger than 0 because we assume the matrix to be invertible. Okay, so this is the model we actually will prove things in, but it holds in general for normal matrices A. Okay. Now I want to know what's the spectrum of our Hamiltonian, and one can easily, by Fourier transform, see that the Fourier transform is in all the components multiplying by these 2 times AK times the cosine. So if you do that, then you notice that the spectrum is just the growth interval from -2a to 2a. But more specifically, one immediately sees the spectrum multiplicity of all these values and looks something like this. So this is the interval between the smallest twice times the smallest eigenvalues of A. You can have double eigenvalues, so we don't require that this is strict. Here's are strict inequalities, and yeah, and well, the cosine gives you always this interval from -2 to 2, and then you just multiply with these factors, and you get something like this for the dimension of this staircase picture for the dimension of for the spectral multiplicity of in the spectrum. Okay. We will see this picture later in another context, so try to remember it. Okay. Now next step, what we wanted to do is decompose the Hilbert space in some way so that H0 looks like just multiplying by E on the decomposition. Well, what's the idea? Well, if H would be finite dimensional, then we would just want HE to be the eigenspace for the energy E. But well, we have absolutely continuous spectrum, so that means that the kernel is trivial, so that will certainly not work. But that gives the idea of what we want to do. So from now on, K will always be either H0 or H. I don't want to write everything twice. So given an energy E and one of the two Hamiltonians, we write GNKE for the space of generalized solutions to the eigenvalue problem. So one can naturally, instead of considering L2 functions, you can naturally consider functions from Z just to values in matrices L by N for some integer N by exactly the same formula as given on L2. And then you consider the generalized eigenvalue equation. And any solution to this eigenvalue equation is uniquely determined by the values in 2 consecutive points, for example, 0 and 1. Since you can just, if you have the value in n-1 and n, you can just calculate n+1 by this formula, where you have to add this term for the interacting Hamiltonian and you leave it for the free Hamiltonian. Okay. And well, but on the other hand, every values in 0 and 1 can be realized. So the dimension of this space is just 2 times L times N. You should think of N to be either 1. So if you have vector valued solutions, or L for L times L matrix, and then you get all vector valued solution by just multiplying a matrix value solution by from constant vector from the right. Okay. The first thing we prove here is it turns out that you actually don't want to give the values in 2 consecutive points, but you rather want to some behavior at infinity. So what we can show is that you can well, you have to have to fix 2 values, because otherwise it's not uniquely defined. But what you can do is, given an energy that's not in the spectrum, there exists a unique function such that the value in 0 is the identity. Now we're talking about matrix valued solution, and that the solutions converge to 0 as you go to either plus or minus infinity. These functions have these solutions have nice properties. Any vector valued solution is the form you take this function at plus infinity times some vector, and plus this function at minus going to 0 at minus infinity times some vector. So these actually span the whole space of the whole 2L dimensional space of solutions of the generalized eigenvalue equation. On top of that, this map is so if you evaluate it in a fixed n, this map is holomorphic, so behaves nice with respect to the energy, and you can approach the spectrum either from, so for me, C plus minus is the upper and lower half plane of the complex plane. So if you approach the spectrum either from above or below, you these limits exist of these solutions, and define functions with exactly the energy that you're approaching. But you get different solutions if you approach from above or from below. And if you are not in one of the thresholds, so where the dimension of the multiplicity changes, then there again this spans the complete space of solutions. But in the thresholds, it's not true. So there you have to complement it by some other solutions. Okay. So this is for the free Hamiltonian. So there and one can actually concretely calculate these solutions. If you're more interested in that, I will explain how to do that in the talk I will give next week in Mexico City. So, but for now, it's sufficient that they exist, and we can concretely calculate them. Okay, so this is the free Hamiltonian. Now we consider the interacting Hamiltonian, and the solutions of the generalized eigenvalue equation for the interacting one are usually called Yost solutions. So this is a theorem about the existence of Yost solutions. And this is saying that for if you take one of these solutions that we proved in the previous slide that they exist, then we can always find a solution of the generalized eigenvalue equation for H, such that approaching either plus or minus infinity, this converges to the identity. So at infinity, the solutions look asymptotically like the solutions to the free eigenvalue equation. Okay. Maybe there should that's a good point to comment about this growth condition I had on the potential. So to have scattering theory, it's sufficient that the potential is just summable, because then Kato-Rosenblum applies and wave operators exist. But what one then cannot do is prove that these solutions here exist and have that property. Why? Because what you essentially do to prove this is you take the solution of the free equation, and then you correct it by adding some terms for each point from the potential. And it turns out that the sum that there appears is precisely the sum that I wanted to converge for our model. And I can actually show that the estimate is strict, so that you cannot improve this. It's not that our estimates are bad and you could improve them, but they actually achieved. So one would have to do something without your solutions if you want a weaker condition on the growth of the potential. So this is where this growth condition enters. Okay, but these solutions exist if you have this strict growth condition, and they also satisfy a nice property, basically the same as before, namely that outside of the spectrum they span the whole set of solutions. And here I forgot to say this is true for everywhere outside of the spectrum of H. So you can in fact have values outside of this interval where this doesn't hold, which is precisely where there are eigenvalues of the Hamiltonian. So in eigenvalues this doesn't hold, but outside of the real line this holds, and this also holds if you're not in an eigenvalue. Okay. And again, this map, if you fix an n and map E to the solution, then this is holomorphic. And again, the limits from above and below exist, and define a solution to the generalized eigenvalue equation for the interacting Hamiltonian. I did not write the last point, which appeared on last slide, that also inside the spectrum dispense all of the solutions, because it's not actually true. It's certainly not true in eigenvalues, which you can have also immersed in the spectrum, but it's even not true for other energies. You can show that the fact that the set where it doesn't span all solutions is a discrete set, but it's not just in the eigenvalues. So that's why I didn't include it here, because it's simply not true. Okay. Now, well, we wanted to decompose our Hilbert space in this direct sum, and well, the first approach was taking generalized solutions to the eigenvalue equation, but well, this cannot be the space that we are interested in, because this space has everywhere the same dimension. It's just 2L. So we have to reduce the solutions we are using, and what we will use is the set of bounded solutions to the eigenvalue equation. Not L2, because that can just happen in actual eigenvalues of the operator, which for H0 there is none. But bounded solutions you can have. And well, we know explicitly our solutions for at least for the free Hamiltonian, and we can just check which one are bounded, and it turns out the number of bounded solutions is precisely the same picture as we had for the spectrum multiplicity of our operator. So every time you pass a threshold, the number of bounded solution goes up by 2, and exactly in the threshold you get 1 more, not 2. So you get this staircase picture where we put these points exactly in the middle of the 2 dimensions. Okay. Well, this shows that if you're not in a threshold and you're in this interval, then the dimension of the space of bounded eigenfunctions is precisely the spectrum multiplicity of that energy, which suggests that HE being this space of bounded generalized eigenfunctions seems to be a good idea, because at least the dimensions match up. Okay. Okay. Now this was the free Hamiltonian. Now we go to the interacting Hamiltonian, and it turns out that you can prove that there is a discrete subset of the spectrum of the free Hamiltonian, which can just have accumulation points in the thresholds, such that outside of this set, the dimension of the set of bounded solutions for the interacting Hamiltonian is precisely the dimension of the bounded solutions for the free Hamiltonian. And okay, they have the same dimension. So the question is, can you map one to the other in a natural way? And it turns out that you can. If you take a solution to the free eigenvalue equation that's bounded, and you do a limiting absorption principle, so you multiply by the resolvent in E plus I times epsilon, or plus minus I times epsilon, and then you multiply with the same with the inverse for the interacting Hamiltonian. Then these limits always exist as long as you're outside of this discrete set D, and in fact define your solution to the for the interacting Hamiltonian. And it turns out that this map actually gives you the isomorphism between these two, but just outside of the set D. Okay. Now we want to use this to actually define this isomorphism from the Hilbert space to this direct integral. And this is the idea is to do some generalization of the Fourier transform, where instead of the normal functions e to the itx, you use these bounded generalized eigenfunctions. And what you do is essentially, well, you want to kind of project to this space, but it's not a part of the Hilbert space. So, well, if it would be a projection, it would look something like this, where BE is a basis of the bounded generalized eigenfunction, so energy E. And what do I mean by this? Well, this actually makes sense if F is a L1 function, because then, well, B is an L infinity function by definition, it's bounded. Then you can take this pairing with an L1 function, and then if you multiply this again with a bounded function, well, you get a bounded function. These bases are finite dimensional, so you can just sum over a basis. And it turns out that if you choose a suitable basis, then you can make this in a way that this operator F0 becomes unitary. Okay. And well, we wanted that with respect to this direct integral decomposition, H0 becomes just multiplying by the energy E. So we can concretely calculate that. Well, if you apply this generalized Fourier transform to H0 times F, well, you get here H0 times F in the definition. But then H0 is self-adjoint, so we can move it to the other side of the scalar product. But B was supposed to be a generalized eigenfunction, so we just get the energy, which shows that it does precisely what we want to do. So if you conjugate H0 with this generalized Fourier transform, you get precisely the direct integral you wanted to have. Okay. So this was for the free Hamiltonian. Now let's look at the interacting Hamiltonian. There we define, we get two generalized Fourier transforms, one's approaching from above and one approaching from below. And we take exactly the same formula, but instead of considering here, instead of projecting on the solutions to the free eigenvalue problem, we project onto the solutions to the interacting eigenvalue problem, which we map the basis to with this limiting absorption principle map to the solutions of the interacting one. Okay. Well, and the most difficult part, which I will not prove now, but just tell you the results here, is to prove that this map, I mean, that's just defined on L1 first, that is actually extends to a bounded operator and satisfies all nice property, but one can't do that. So one can show that if you compose this with its star in this way, then you actually get the identity. And if you compose the other way around, well, you don't get the identity, so it's not unitary, but it's a partial isometry going to the absolute continuous spectrum of H. Which, well, in the free case, it's also going to absolute continuous spectrum, but it's the whole Hilbert space, so you don't see them. Okay, and then by the same calculations before, one sees that if you conjugate H by these generalized Fourier transforms, you also get the multiplying by the identities. Exactly the same calculation. And well, we have two of them, so we kind of have to say how they relate to each other. And it turns out, well, that one is a multiplying by something of the other, where, well, for one you have here this phi plus, and for one you have phi minus. So if you define SE to be the transformation matrix with respect to phi minus inverse phi plus, then, well, you can write F minus as F plus times this direct integral over these matrices here. Okay. So far, this notation is not justified because it's just the matrix I introduced, but we will later see that this coincides precisely with the scattering matrix. Okay. Okay, and then one can prove the thing wants to see, which is now we can explicitly calculate the wave operators. Well, they are given by taking these generalized Fourier transforms for the interaction Hamiltonian, a star, and multiplying it with the generalized Fourier transform for the free Hamiltonian. And this is how you can calculate the wave operators. and then you get the scattering operator with respect to the Fourier transform for the free Hamiltonian precisely diagonalizes and gives you exactly these matrices SE that we introduced in the slide before. How do you prove that? Well, for omega plus, you have this integral e to the minus it Hamiltonian, and on the right-hand side, well, here we had the limit in the absorption principle, and the idea is you use this equation that relates the one parameter group to the resolvent, and you exploit it in a very standard way that you, for example, you can find in Reed-Simon or whatever you prefer to relate this limit to this limit, and thereby you can prove this. It's not so easy, but one can do it exploiting this relation here, and then it's an easy way to calculate S. Well, you just plug in this formula here, and then multiplying by F0 from both sides, you get the S conjugated by the Fourier transform is just this product here, and then you plug in the formula from before relating F minus to F plus, and then you use that this here was the identity to prove that in fact S does decompose in this way, precisely with the matrix SE that we defined before. Yeah.
Using these direct integrals and so forth, which I'm used to in the L2 context. Yeah, is it? But then we're looking at bounded solutions, and these are other spaces. Or are you now back in square summable? I mean, operators acting on square summable.
Yeah. So the generalized Fourier transform are acting on L2.
Okay. Yeah.
Well, maybe you can go back to where they were defined. So you take, I mean, as always, you define Fourier transform on L1 and then show that you can continue to L2. And well, for L1, this is L infinity because it's the bounded solutions. L1, so this makes sense. This is a finite sum. This makes sense, and then I can multiply by this, which gives me again a bounded function. So it maps the set of bounded generalized eigenfunctions to itself, and well, and then you prove these things here, which indicates that you can actually make sense out of it for a function L2. Which we have because all these spaces are finite dimensional, so there's no problem. Does that answer your question? Or? Okay. Okay. Where were we? Okay. Now this is the part about making sense of the calculating the scattering matrices. So I promised you we will prove some type of Levinson theorem. And for this, I have to introduce a concept which is the Wronskian for our model. So what is that? Well, if you have any two functions from Z to C to the L, we define the Wronskian as well, this formula, which is you take the value of one solution at n plus 1 and take the scalar product with A times the other solution n, and then you invert the roles and subtract that. And this quantity is important. And what happens is if you have two solutions, so this was for general functions, you can define that. But if you have two solutions to an energy and the conjugated energy, you can actually show that this quantity here is independent of this value n. So in the following, I will just omit this n here because it's independent. Okay. And to not always write so much, I introduce a short notation. So I write WE for the Wronskian of the solution at energy. So these U's were the Yost solutions that we proved before that exist. And you take the Wronskian of the solution that looks that looks like the solutions of the free eigenvalue equation at plus infinity with the solution that looks like the free eigenvalue, like the free solution at minus infinity at the conjugated energy. And well, these are solutions to the eigenvalue equation, so this is independent of n. So this kind of relates the ones with the behavior at plus infinity to the ones with the given behavior at minus infinity. And well, since the U's have limits to the spectrum from above and below, one can do the same for a Wronskian. So I write WE plus minus for these limits from above and below of this Wronskian. Okay. And well, now we wanted to calculate the integral over the scattering matrix, and it turns out that if you're not in the discrete set D that I mentioned before, where things fail, but well, it's discrete, so we can ignore it. Then it turns out that you can actually calculate the determinant of the scattering matrix using the determinant of these Wronskians from above and below. It's just the quotient of the two times -1 to the power of the dimension of the space of boundary. Okay. And okay. What we wanted is actually the logarithmic derivative of that. So, but it's an easy corollary. Well, the logarithmic derivative makes out of quotients, it makes differences. So you can calculate this quotient here by just taking the difference of the logarithmic derivative of the Wronskian approaching from below and approaching from above. Okay. Now, well, we want to calculate the integral, and now I will explain you the objects necessary to say what's on the other side of the equation, and then we prove that they are actually equal. So, well, as I said before, you have the limits from above and below of the generalized of the solutions, and then you can ask, well, when are they equal? I mean, in general, I told you they are not equal, and that's true, but maybe for some multiplying from some vectors to the right, they are equal. So I define v plus minus of e for all the vectors such that the limits from above and below are actually producing the same solution. Well, this is a subspace of CL, and then I define h plus minus for actually the space of these solutions that you get by approaching up from above and below. Well, then it doesn't matter if you define it like this or like this, because approaching from above and below and anyways gives you the same solution. So this is, and you do this as plus and at minus infinity. And then you define h to be the intersection of the ones that look like this at plus infinity and the ones that look like this as minus infinity. If you cannot really imagine something from that, one can actually show that this is something like the solutions that behave like constants at plus infinity or minus infinity. Which, of course, if they look like constants, well, one constant is 0. So one can show that this space actually includes, if there is an eigenvalue, it includes the kernel. In general, it just includes it, but if you are outside of the threshold, one can actually show that it is the kernel. What I will define is I write JB of E for bound states for precisely the dimension of the kernel in some energy E. And well, in general, this is just a subspace of this space HE. You will later see why I defined this space. So, well, I define just JH for half bound states as the dimension of the quotient. So the dimension of this space minus the dimension of this space. These quantities will appear later when we evaluate our integral. Okay, and so this I do in every energy E, and then I define JB, so all bound states for every energy is just summing up over all R, and one can show that this sum here, even though it's over all R, it's actually a finite sum. And the same I do for the half bound states. Well, they can anyway just appear in the thresholds, which are finitely many. So, okay. Now, I tell you what these numbers we just defined have to do with the Wronskian. So the Wronskian locally Well, if you have an energy where these numbers JB and JH are not zero, then they produce zeros of the Wronskian in these points. And this theorem, this proposition tells you the degree of the zero it produces. And it turns out that bound states, so actual eigenvectors, generate a zero of degree 1. So that you locally can write a determinant of the Wronskian as Z minus E times to the power of the dimension of bound states, and the half bound states generate you zeros of order square root, so of degree 1/2. Okay, where here by square root I denote some suitably chosen branch of the complex square root. So locally the Wronskian is of this form, and then well we are actually interested in the logarithmic derivative of that. So well, but that's an easy corollary. I mean, if you just take this and calculate logarithmic derivative, you get that it looks like this. I mean, the square root gives you a factor of 1/2 to the exponent here, and products go to sums. So we have this part coming from here, and the logarithmic derivative of f coming from here. Okay. So what this means, one can easily show that this is not really important because it's non-zero in the energy we're considering. So in the limit, like if you integrate this quantity over some ball, then this just vanishes, and integrating this, well, you get this factor, and the integral over 1 over Z minus E along some circle around E is just 2 pi I. So we already can integrate this logarithmic derivative we're interested in along some circles around energies. Okay. Now I tell you the theorem. So the theorem is the following. This integral, you can calculate it. It gives you precisely the number of bound states plus half times the number of half bound states minus L, which was the dimension of degrees of freedom, well, with minus sign in front. Now, the integral itself doesn't exist, but this here says that it exists in the form of a principal value. So what you do is you, instead of integrating a spectrum, I put this epsilon here, which is you integrate over all points that have distance at least epsilon from the thresholds, and then you let the limit go to 0. So you basically consider it as a principal value in all the points of the threshold. And in this way, it exists and gives you precisely this value. So from the scattering matrix, you can recover like the data about the model, number of eigenvalues and eigenvectors and half bound. So let me give you a quick idea of the proof. Well, first we use that we can write the logarithmic derivative of the scattering matrix as the difference of the logarithmic derivatives of the Wronskian. And then this means that integrating that the left-hand side is the same as integrating the Wronskian over the following path. So on top, remember it was W minus W plus. So on top, we are integrating to the left, and on the bottom, we're integrating to the right, and we leave out these epsilon balls around the thresholds. Okay. Now I will, from each slide to the next, change the path until we arrive at something we can actually calculate. So the first thing we'll do, there may be immersed eigenvalues which produce the summands for the bound states. But what can show that in small balls around these immersed eigenvalues, the integral on top and bottom, actually the difference goes to 0. So what I can do is just remove also the balls around these immersed eigenvalues. That does not, in the limit, does not change the integral. And then the next thing I will do is outside of the spectrum, while the limits from above and below are the same, because it's holomorphic outside. So it does not matter if I approach from above or below. So what I can also do is just add some integration here because I integrate on top to the left and bottom to the right, they just cancel out. And I integrate up to some r, which is just chosen in a way that outside there are no more eigenvalues. For example, twice the norm of H0. And I leave out also epsilon balls around eigenvalues that could be outside. Okay. And now what I now do is consider the following closed path. So you go here around, then you always work on straight lines, and then if you reach immersed eigenvalue outside or a threshold, then you just go in a small epsilon circle around. Well, this is a closed path, so the integral over all this is 0. And you do the same on the bottom, and it turns out, well, these where you integrate on straight lines are precisely integral we had before, but in the other directions. So that's why I put them dotted, because they cancel out with what we had before. So the integral we had before is equal to integrating over all these circles. But we know how to evaluate them. So this limit here, well, in the small circles, we already established that this gives you the number of bound states in that energy plus half times the number of half bound states. And the big circle gives you the order of the pole at infinity. You can just put the radius to infinity. And well, then you sum these up, and it turns out that the order you can explicitly calculate it's L. And well, this gives you precisely the formula of the theorem. So thank you for that.
Are there any questions? Well, I have a question for the construction of the generalized Fourier maps. Which is the condition you use in the potential V?
The condition I used, I showed you in the first slide.
Not just the L1, but some n norm of Vn, right? So could you show the condition?
Yes.
Because there are two.
But I think you could probably, if you knew by some other way that the Yost solutions exist, you could probably do the Fourier part with just supposing that the potential is L1.
This is what I believe is true.
Yeah.
You should not need L11.
Yes, but you need it for having the nice properties of the Yost solution.
Yeah, but you may do this without using the Yost solutions.
Yes. Yes.
By a different method. Okay, any question? Any further question? Okay, well, we thank the speaker again. And we meet in the afternoon. I think it's at, let me see. At 3:30 then. Okay.